When an op-amp is operated without feedback or open loop, the output is driven between maximum and minimum values as imposed by the DC supply values. Although this operation is not desired for most linear uses, it is well suited for digital applications where highest and lowest values can represent binary values of 0 and 1. Let's first discuss the simple zero-level detection comparator. The following figure illustrates a comparator which determines when an input voltage exceeds a certain level. The inverting input is grounded and the input signal is connected to the non-inverting input. Since there is a very high open-loop gain, a small voltage difference between the two inputs causes the amplifier to be driven into saturation, thereby causing the output to be maximum. For example, if we consider an op-amp having a gain of 100,000, a voltage difference of a mere 0.2 millivolts between the inputs could produce an output voltage of 0.2 millivolts times 100,000 or 20 volts. However, since most op-amps have output voltage restrictions of plus or minus 15 volts because of their DC supply voltages, the device would be driven into saturation. Let's next look at the non-zero level detection comparator. The zero level detector in the previous figure can be modified to detect voltages other than zero by connecting a fixed reference voltage source as shown in the figure. A practical way to set the reference voltage is to use a voltage divider whose reference voltage, V sub ref, may be determined by multiplying R2 by the source voltage plus V and dividing by the sum of R1 and R2. For example, in the above figure, the input signal shown is applied to the comparator circuit. Find Vref and make a sketch of the output waveform. Assume the maximum output levels are plus and minus 12 volts. The reference voltages set by R1 and R2 may be determined by multiplying R2, the 3 k ohms, by the source voltage 9 volts and dividing by the sum of R1 7.5 k ohms and R2 3 k ohms, which equals 2.57 volts. Each time the input is greater than plus 2.75 volts, the output voltage switches to its maximum level, plus 12 volts, and each time the input goes below 2.57 volts, the output is driven to its minimum or minus 12 volt level. The waveform is shown in the figure now shown. We will now discuss how to reduce noise effects with hysteresis. A method incorporating positive feedback, termed hysteresis, can be used to make the comparator respond less to noise. Basically, hysteresis implies that there is a higher reference value when the input voltage goes from a lower to a higher level than when it goes from a higher to a lower level. A familiar example of hysteresis is the household thermostat, which turns the heater on at one temperature and off at another. The two reference levels pertaining to our discussion are the upper trigger point, called UTP, and the lower trigger point, called LTP. A positive feedback arrangement establishes this two-level hysteresis effect. The non-inverting input is connected to a resistive voltage divider, and a portion of the output voltage is fed back to the input. The input signal is applied to the inverting input in this case. Assuming the output voltage is at its positive maximum, plus V out max, the voltage fed back to the non-inverting input, V UTP, is determined by multiplying R2 by the maximum output voltage, plus V sub O max, and dividing by the sum of R1 and R2. When the input voltage, Vin, is greater than V UTP, the output voltage drops to its negative maximum, minus V out max. The voltage fed back to the non-inverting input is VLTP, as is determined by multiplying R2 by the maximum output voltage minus V out max and dividing by the sum of R1 and R2. The input voltage must now be less than VLTP for the device to switch back to its other state. This indicates the small amount of noise voltage has no effect on the output. A comparator using hysteresis is also known as a Schmitt trigger. The amount of hysteresis is defined by the difference of the two trigger levels. For example, determine the upper and lower trigger points for the comparator circuit in the figure shown. Assume that plus V out max equals plus 6 volt and minus V out max equals minus 6 volts. VUTP is determined by multiplying R2, 200 ohms, by the maximum output voltage, 6 volts, and dividing by the sum of R1 and R2, 200 ohms plus 200 ohms, or 3 volts. VLTP is determined by multiplying R2, the 200 ohms, by the maximum output voltage, minus 6 volts, and dividing by the sum of R1 and R2, 200 plus 200 ohms, or minus 3 volts. Let's now discuss the parameter called output bounding. In certain applications, it is necessary to limit the output voltage levels of a comparator to a value which is less than the saturation value of the OPAmp. A single Zener diode can be used to restrict the output voltage swing to the Zener voltage in a particular direction and to the forward voltage drop of the diode in the other direction. The limiting of the output range is called bounding. The anode of the Zener is connected to the inverting input and is essentially at ground potential, or 0 volts. Thus, when the output reaches a positive value equal to the Zener voltage, it limits at that value. When the output swings to a negative value, the Zener operates as a regular diode and becomes forward biased at 0.7 volts, limiting the output swing negative to the same value. Turning the Zener around limits the output in the reverse direction. For example, determine the output voltage waveform for the figure now shown. Calculate V UTP and V LTP. On observation, we find that the comparator uses both hysteresis and Zener bounding. The voltage across D1 and D2 in either directions is 4.2 volts, that is, 3.5 volts plus 0.7. This is because one Zener is always forward biased with a drop of 0.7 when the other is in breakdown. The voltage at the inverting OPAmp input is V sub 0 plus or minus 4.2 volts. Since the differential voltage is negligible, the voltage at the non-inverting OPAmp input is also V sub 0 plus or minus 4.2 volts. Therefore, the voltage across V sub R1 is plus or minus 4.2 volts. The current through R1 is equal to the voltage V sub R1, 4.2 volts, divided by R1, or 200 ohms, which equals 21 microamps. Since the current flowing into the non-inverting input can be neglected, IR2 is approximately equal to IR1, or plus or minus 21 microamps. VR2 is equal to R2 85 kiloohms times IR2 21 microamps, or plus or minus 1.8 volts. The output voltage is equal to VR1 plus or minus 4.2 volts plus VR2 plus or minus 1.8 volts, or 6 volts. The upper trigger point is determined by multiplying R2 85 kiloohms by the maximum output voltage 6 volts and dividing by the sum of R1 and R2, 185 kiloohms, or approximately 2.8 volts. The lower trigger point is determined by multiplying R2, 85 kiloohms, by the maximum output voltage minus 6 volts and dividing by the sum of R1 and R2, 185 kiloohms, or approximately minus 2.8 volts. The output waveform will look like the figure now shown.